In this video, I'll be designing, building and testing an autonomous boat which runs on solar power. The goal is to build a boat which is mathematically as efficient as possible. This is also my first proper boat build, so there was a lot I had to learn first. To make a reasonably efficient boat, you have to fight physics. Speedboats use a planing hull. They ride on top of the water with high Freud numbers. It's fast, but it eats batteries alive. The boat we're gonna build is gonna be as efficient as possible and travel slowly with low Freud numbers, so we'll use a displacement hull which slices through the water efficiently. I decided to make this boat a catamaran because catamarans are really stable, which allows us to mount a large solar panel on top. Because fluid dynamics is brutal, I couldn't just guess the pontoon shape, so I made a Python script to do it for me. To find the perfect shape, I used something called Latin hypercube sampling. It's like throwing darts evenly across a whole board in a multi-dimensional cube to find the best scoring areas. The script takes my variables like length, width, draft, displacement and the prismatic coefficient and generates 10,000 completely random but evenly spaced hull shapes and then selects the best one with the least wave-making drag and skin friction for our chosen displacement, velocity and waterline length and then exports it as curves to CAD. To increase longitudinal stability, I had to make it 1 meter long, which reduced the total efficiency by around 10%, which is a good trade-off for stability. CFD confirms the optimized hull's efficiency. The bow wave is basically flat, and there's no significant flow separation at the back. Because we minimized the wave-making drag, almost all the drag left is due to skin friction between the hull and the water, which means that we need to make the surface as smooth as possible. To get that smooth surface and the exact geometry, I have to build it as perfectly as possible. I decided to print the hulls out of PETG with a 1-layer wall thickness and a low infill, which will act as a stay-in-place mold. This allows me to get the perfect geometry as well as make the hulls as lightweight as possible and integrate mounts for the motor and everything else directly into the hulls themselves. I glued everything together with CA glue. After gluing everything together, I now had 2 lightweight but strong stay-in-place molds, which will also work as the structure for the hulls. In the past, I've used this same technique for UAV construction. To get rid of the seams, I used some filler to cover them, after which I sanded everything as smooth as possible. This turned out really smooth. To reinforce the hulls, I decided to use this thin and lightweight 25 GSM fiberglass cloth, which was cheap, and because the thinner the cloth, the easier it is to apply to complex geometry. For laminating the fiberglass, I used some 2-part epoxy resin, as epoxy is far stronger, easier to work with and more stable in every metric compared to polyester resin, which gives off more unpleasant fumes and is far more brittle than epoxy. I then cleaned everything up and cut off the excess material with a scalpel. Then I put another coat of just epoxy on top, which would reinforce the fiberglass layer beneath it and make everything waterproof and give us a nice hard surface to work with. And after that, I cut off the rest of the excess material from the hulls, after which I applied some spray filler to fill in any possible pinholes and defects before wet sanding it with 280 grit sandpaper until the surface was completely smooth. Before applying any paint on top, I wiped everything down with acetone to remove any dust and oils which would detrimentally affect the surface adhesion. I used some alkyd-based smooth metal paint and applied it with a brush. But in hindsight, this was a huge mistake, and I should have used a roller to apply it more evenly instead. Yeah, this didn't turn out all that good. It started dripping down the sides. I think I'll now sand it and then try spray painting it. After waiting for almost a week for the alkyd paint to cross-link and harden enough, I wet sanded it again, which took a long time by hand, and then I put many thin layers of alkyd spray paint on top until the surface was near perfect. I was happy with this result, as it was hydraulically smooth despite not being glossy. For the lid, I cut some 6mm thick, very lightweight balsa sheet and drilled some holes into it, after which I painted it with the same alkyd spray paint. This made the surface waterproof and hard. To attach the lid, I had to make some mounts, so I 3D printed them and put some M5 brass heat inserts with threads in there. And in total, I had to make 32 of them, which took a while. I attached them to the hulls with some 2-component epoxy, which holds them firmly in place. The lid just goes onto there like that, and then is held on by M5 machine screws and washers. For the frame, I got some 10mm square aluminum tubing and printed these connector parts, which allowed me to easily construct a rigid frame by gluing them together with some more 2-part epoxy. To hold the solar panel in place, I made these parts which go onto there like that, and then I put a M2 brass insert in there. The frame turned out surprisingly rigid and strong, yet lightweight. For propulsion, I'm using these 5010 360 kV flat drone motors, which I'll run on 3S voltage. They're really efficient because they have a lot of torque at low RPM, which is what I want. The motors are connected to the propeller using this drive shaft, which I filled with marine grease to keep most of the water out. I attached it to the hulls using some more epoxy, which also waterproofs it. I picked a 38mm 3-blade propeller because it hits the exact balance of efficiency and thrust. The motor runs optimally at around 2500 RPM, and my CFD simulation showed the Catamaran hulls at 1 meters per second only generate less than 0.5 newtons of drag each. At that low resistance, the absolute minimum prop I need is about 37mm, but I intentionally oversized it to a 48mm 3-blade, as a larger propeller spinning slower is much more efficient. This setup lets us easily hit our target speed while maximizing battery life. I also added a bilge pump system inside the hulls, which uses tiny 5V submersible pumps connected with some tubing to a hole in the back where any water is thrown out from. The pumps are gonna be activated by some 5V relays, which will be activated by water level sensors, which will send a signal to a Raspberry Pi. After having finished the pontoon and frame assemblies, I attached them together. The frame is held in place by some machine screws. This boat will also use differential thrust for steering, which means we don't need any separate rudder, which would add drag. The autopilot system I'm using is the F405 Wing V2, connected to a M10Q compass and GNSS module and an ELRS 868 MHz receiver. This is actually the same system I used in my first unsuccessful boat a year ago, as well as in my cargo UAV, so it's been through quite a lot. As the solar panel, I'm using this 100W ETFE panel, which is flexible and lightweight, weighing only 1.1 kilograms. It's quite a bit overkill, but that means it will provide enough power even on slightly cloudy days. It will be connected to this 3S 3A MPPT solar panel controller, which is connected to this 3S balance charger, which will be connected to the battery. I mounted everything inside this waterproof plastic box. As the battery, I'm using this 3S 3P 15Ah battery pack, which was made before I had the proper spot welder. A lead already came loose and I had to fix it, so let's hope that won't be an issue later on. The battery just goes into there like that and plugs in like this, and then we can turn on the system from this cool switch I added. To get telemetry, I'm using this ancient 433 MHz telemetry radio. I could have used DLRS for the Mavlink telemetry, but my TX module is too old to support it. In the next video, I'm planning to add the Raspberry Pi to this boat and connecting it to a 4G modem for infinite video and telemetry range. But for now, during initial testing and tuning, I'll have to stick to this old telemetry radio. The total mass came out to less than 5 kilograms, which is excellent. For transportation, I built this cart for it, which I dragged through all sorts of terrain, but eventually I did get it there, and it held up just fine. This day, the weather was very calm and the lake was almost perfectly still, which was perfect for testing. It's a bit cloudy today, so the solar panel isn't gonna produce that much power. I estimate at most 20 to 30 watts, but that should be plenty, as we're just tuning it for now. I also set up this inflatable boat in case it gets stuck out there, but let's hope it doesn't. Oh, there's a duck. Oh, it actually floats. It seems to be working. I'll first do a short test drive just to see if it's waterproof. Doesn't look like it's filling with water. It worked perfectly. I think I'll tune it some more now and then do a couple auto missions maybe. I was surprised by how stable the boat was. Even when driving in manual mode, it maintained a completely straight line while driving forward. This is probably thanks to the sharp keel at the bottom and the Catamaran configuration, which add a lot of lateral and roll stability to the boat. It's really efficient. It travels 1 meters per second at less than half throttle, and it only draws less than 3 amperes, 2.5 actually, meaning that it's around 2.4 times 12, less than 30 watts, which is really good for a boat this size. So this telemetry radio I'm using absolutely sucks. At only like 30 meters, it already lost signal. Oh, it regained it. And I forgot to calibrate the gyroscope at home, so I can't switch to any auto modes. meaning that I have to drive it in manual for now. Because I had forgotten to calibrate the compass and flight controller at home, the EKF was all over the place and the flight controller had no idea what its heading, or altitude or attitude was. Here you can see just how messed up the telemetry is and how it's pointing all over the place. To fix this is very simple, I just have to calibrate the flight controller and compass module properly at home. The boat just slices through the water, and the bow wave has a very low amplitude, and most of the transverse waves destructively interfere, leaving primarily the divergent waves of the Kelvin wake visible. And all of this is exactly what we wanna see. The boat also turns surprisingly well for a catamaran with differential thrust steering. So, luckily we didn't need this inflatable boat, and everything seems to have stayed dry inside. So this was a success. So, the boat traveled at 1 meters per second at less than 30 watts, which means that the solar panel probably made more than the motors used. I didn't get any precise charging data from the solar panel, as I don't have the Raspberry Pi hooked up yet. But in the next video I'm gonna hook that up and make this controllable by 4G. Overall, I'd say this boat turned out exceptionally good for my first proper boat. If you like this video and wanna see the next part where I upgrade this boat, make sure to like this video and subscribe. Thanks for watching and see you in the next one.